Section 5.1 Polynomial Functions. Today, students will be able to classify and graph polynomials and be able to describe their end behaviors. A polynomial is a monomial or the sum of monomials. An example of this would be maybe 2x cubed. Or, if we were talking about sums, 3x squared plus x minus 5. Either one of those are polynomials. The degree of a polynomial is going to be the greatest exponent in each monomial term. So if I were to give you 5 plus 4x cubed minus 3x plus 6x to the 5th power. You're looking for the monomial that has the greatest exponent, and then since 5 is your largest exponent, this polynomial has a degree of 5. You don't care about any of the other exponents, you just care about the highest exponent. Standard form of a polynomial function is going to arrange each term by degree in descending order, so from highest degree to lowest degree. An example of this would be like 3x to the 4th minus 2x to the 3rd plus x minus 7. It goes from an exponent of 4 all the way to no exponent at all, so it's in descending order. Now let's learn how to classify each polynomial. We are first going to look at how we classify polynomials based on the degree that's given. So if a polynomial has a degree of 0, this is called a constant. An example of a constant would just be some number, maybe like the number 2. Since it has no exponent, that's what makes it have a degree of 0. Now if a polynomial has a degree of 1, that is considered to be linear. An example of a linear term could be 3x plus 4. The exponent on the x is an invisible 1. If the degree is 2, it's considered to be quadratic. An example of a quadratic function could be x squared plus 2x minus 3. The highest exponent on the x is a 2. 3 is considered cubic. An example of something cubic is 8x cubed minus 27. The highest exponent is a 3. With a degree of 4, this is called quartic. And an example of a quartic polynomial could be x to the 4th minus 16. And the last one we look at is with a degree of 5, and that's called quintic. Example of a quintic polynomial could be x to the 5th plus 2x to the 4th minus 5x cubed. Okay, again, all that matters is the highest exponent, and the biggest exponent is a 5, so therefore it's considered to be quintic. We classify polynomials by degree and the number of terms, so now we are going to look at all the different names for all the number of terms. So if there were 0 terms, there would be nothing there, so therefore we don't talk about that one. The first one we talk about is if they have 1 term, and if there's 1 term, it's considered to be a monomial. An example of a monomial could be 5x. 2 terms is considered to be a binomial. An example of a binomial could be x squared minus 16. There's just 2 things, the x squared and then the 16. 3 terms is considered a trinomial. We've been looking a lot at trinomials, so x squared minus 5x plus 6 is an example of a trinomial. There's the x squared, the 5x, and the 6. There's 3 different things there. 4 or more are kind of all lumped together in one thing, and we call that a polynomial with, and then I'm going to write a blank and then terms. So depending on what the example is, however many terms we are, you fill in that blank. So for instance, if I were to give you x to the fourth plus 3x squared minus 6x plus 7, okay, there's the x to the fourth, the 3x squared, the minus 6x, and the 7. So we would call this a polynomial with 4 terms. Let's look at how we classify this polynomial based on its degree and number of terms. So we're given 3x cubed minus x plus 5x to the fourth. So first thing you want to do is write it in standard form with the highest exponent first. So 5x to the fourth, and then remember we go in descending order, so then plus 3x cubed, and then minus x. So what I mainly care about is my highest exponent. The highest exponent is a 4, and so when we classify it based on the degree, 4 represents the word quartic. Okay, then the number of terms, there's the 5x to the fourth, 3x cubed, and then the minus x, so since there's 3 terms, this is considered a quartic trinomial. Press pause, and I want you guys to try 3 minus 4x to the fifth plus 2x squared plus x plus 5x cubed plus 10. Again, we are going to classify it by its degree and how many terms it's given. First thing you're going to want to do is write this in standard form, so I need to start with my highest exponent first. So negative 4x to the fifth comes first. And then after x to the fifth comes plus 5x to the third, and then plus 2x squared, and then plus x. And if you notice, you have the 3 and you have the 10, so we need to combine those. 3 plus 10 gives me 13. Okay, so the highest exponent is a 5, so this is considered quintic. And then 4x to the fifth, 5x to the third, 2x to the second, x, and 13. There's 1, 2, 3, 4, 5 terms. So we consider this a quintic polynomial, and then with 5 terms. Now let's talk about the end behavior of polynomials. And end behavior is what's happening at the ends or the edges of your graph. So if we think about something that's even, an example of a polynomial that has an even degree could be x squared, x to the fourth, x to the sixth, anything with an even exponent as its highest exponent. Okay, so we only really know what x to the second looks like, and if you were to envision x to the second, that's a parabola, and your graph looks like this. So again, I said that it was the end behavior, so we only care about what's happening at the ends. So I'm going to go ahead and I'm going to erase all of this in the middle. So the end behavior of even positive polynomials is that they are both pointing upwards. In the book it says up and up, but we're going to write it differently than that. So as x goes to negative infinity, f of x goes to, and negative infinity is talking about the arrow on the left hand side. Since it's pointing up, it's going towards positive infinity. Okay, then the other side, as x goes to positive infinity, f of x goes to, now we're talking about the arrow on the right since it's positive infinity. So on the right, my arrow is also pointing up, so it's also going towards positive infinity. Okay, now when we look at the even negatives, An example of that would be negative x to the second, negative x to the fourth, negative x to the sixth, and again, so on. And I'm really only going to focus on this negative x to the second since we know the most about that one. So that negative out in front takes our parabola and flips it over. So again, I only care about what's happening on the end, so I'm going to erase all of this in the middle. So now both of my arrows are pointing down and down. So as x goes to negative infinity, so that's the arrow on the left, f of x is going, since my arrow is pointing down, it's going towards negative infinity. And then as x goes to positive infinity, f of x is going too. So now I'm talking about the arrow on the right, since we're talking about towards positive infinity. And since that one is also pointing down, it's going towards negative infinity. Now let's talk about the end behavior of odd polynomials. So we're going to start with odd positives. So if we think of examples of polynomials that have odd degrees, we're going to start with x because remember it has an invisible 1. And then it goes to x cubed, x to the fifth, and so on. Okay, you know what just x looks like if we were to graph it. That would be a line of some sort. And since we're talking about the end behaviors, I'm going to erase everything that's in the middle of my graph. Okay, so on the left-hand side, my arrow is pointing down. On the right-hand side, my arrow is pointing up. So the book calls it down and then up, but we are going to write it in interval notation. So as x goes to negative infinity, f of x goes to. So negative infinity is talking about the arrow on the left. Since it's pointing down, it's also going towards negative infinity. Now as x goes to positive infinity, now we're talking about the arrow on the right. F of x goes to, and since the arrow on the right is pointing up, it's going towards positive infinity. Examples of polynomials that have odd degrees but are negative would be negative x cubed, negative x to the fifth, and so on. Okay, negative x, remember that negative just flips it over, so now my arrow is pointing the opposite way. Don't care about what's happening in the middle, just care about what's happening on the edges. So on the left-hand side, my arrow is pointing up. On the right-hand side, my arrow is pointing down. So this is up and down, the book calls it. So as x goes to negative infinity, f of x goes to, okay, negative infinity is talking about the arrow on the left. Since my arrow is pointing up towards positive infinity, it's going towards positive infinity. So now as x goes to positive infinity, now we're talking about the arrow on the right, f of x goes to, so now since my arrow is pointing down, it's going towards negative infinity. The number of turning points is going to tell you the number of times that your graph is going to change directions. So to determine the number of turning points, you take the highest degree, the highest exponent. You are always going to subtract 1. That's going to be your first number of turning points. And then to find the rest of them, you're going to have to look at a graph, but just know that you can always take away 2 until you reach 0. So let's look at an example of this. So if I were to give you y equals 2x to the fourth plus x cubed minus x squared. Okay, so the only thing you care about is the highest exponent. So, since my degree is 4, you take 4 and you are always going to subtract 1. So, 4 minus 1 gives me 3 turning points. After you get your maximum number of turning points, you're going to take that number and then you are going to subtract 2 until you reach 0. So, 3 minus 2 gives me 1, and then I would try to subtract 2 one more time, and that's going to give me a negative number, so I'm going to stop. So the number of turning points this graph is going to have is it's either going to have 3 turning points or it's going to have 1 turning point. Okay, let's use this example to also help us determine the end behavior. So again, my highest exponent is a 4, and 4 is an even number. And then I have to look at the a in front. Since 2 is positive, this is an even positive polynomial. So even positive, remember, looks like this. You only care about what's happening at the ends. So as x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to positive infinity. Press pause and I want you to determine the number of turning points and the end behavior of the polynomial y equals negative x cubed plus 4x squared minus 2x plus 1. So to determine the turning points, we are going to look at the highest exponent. The highest exponent is a 3. So I start with 3 and I always take away 1 to begin with. So the maximum number of turning points that this graph could have is a total of 2. Now you take the answer you got and you are always going to subtract 2 after that. So 2 minus 2 gives you 0. Now since I reached 0, I could have 2 turning points, or I could have 0 turning points. The only way you can determine whether it's 2 or whether it's 0 is to pull out your graphing calculator and actually take a look at it. Alright, now let's talk about the end behavior. So the highest exponent is a 3, which is an odd number, and then since there's this minus sign out in front, this is an odd negative. So odd negatives, remember we drew the picture, it's the line flipped the other way because the minus sign flips it over. I only care about what's happening at the ends of it. So as x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to negative infinity. Our last example today, we are going to be using differences to determine the degree of a polynomial. Okay, so you are given a table of values to determine whether these points give you a certain type of polynomial with the degree. So we are going to take the two y terms, we only care about the y terms, and we are going to subtract them to get the difference. So I'm going to start with the bottom y term, so negative 16 minus 23 gives me negative 39. If you were to do 23 minus negative 16, you would get the similar outcome. Your signs are just going to be different for a while, but again, your end answer is going to be the same in case you forget. Okay, this is where most students make a mistake. They jump and they do 15 and 10, but you have to do 16 and 15. So negative 15 minus negative 16 gives me 1. Okay, now we need to look at the difference between negative 15 and negative 10. So we do negative 10 minus negative 15 and we get 5. Now negative 13 minus negative 10 and we get negative 3. Negative 12 minus negative 13 and we get 1. And then 29 minus negative 12 and we get 41. Okay, since none of those numbers are the same, we have to, not the 1 and the 1 are the same, but they are not all the same, so we have to keep going. So now we do it again. 1 minus negative 39 gives me positive 40. 5 minus 1 gives me 4. Negative 3 minus 5 gives me negative 8. 1 minus negative 3 gives me 4. And 41 minus 1 gives me 40. Again, all of those numbers aren't the same, so we subtract again. 4 minus 40 gives me negative 36. Negative 8 minus 4 gives me negative 12. 4 minus negative 8 gives me positive 12. And 40 minus 4 gives me positive 36. Again, not all the same numbers, so we subtract one more time. Negative 12 minus negative 36 gives me positive 24. 12 minus negative 12, also positive 24. 36 minus 12 also gives me positive 24. So, since all of these numbers are the same, that's when you know to stop. You subtracted once, twice, 3. It took 4 times until you got all of the same answers. So this has a degree of 4 since you subtracted 4 times until you got the same answer.